Okay, today class we're going to talk about a theorem that's fundamental to group theory that involves homomorphisms. So we're going to let phi be a homomorphism from group G to group H, and we're just going to use multiplication and just by juxtaposition instead of writing symbols for this. And we're going to let K be a subgroup of G, and we're going to find phi of K. That's all the things that K maps to, essentially. So it's a set of Y in H, so it's a range set, for which phi of B equals Y for some B in K. Like I say, that all that's really saying is it's the set of things that K maps to in H. So we're going to show phi of K is a subgroup of H. And the big deal about this theorem is we're showing that subgroups map to subgroups via a homomorphism. Okay? So let's list some things we can use in this proof and talk about it before we do it. So the big facts, all right? Phi of AB is equal to phi of A times phi of B. All right? That's a definition of a homomorphism. All right? We know that for all A and B in K, that means A, B inverse is in K. Okay? And that's a theorem. That's a theorem about subgroups, and we're going to need that in our proof. Okay, that's also how we're going to prove this thing. All right? We know that another important thing to know, phi of A inverse is equal to phi of A whole thing inverse. All right? So those are going to be the key big things, and sort of the idea here is we have our two sets. So this is G and this is H, and F connects them. And we already know that we have the identity elements in each one, and we know that the identity of one maps to the identity of the other. So we also know that we have the subgroup K. All subgroups have the identity in them. So that whole subgroup is essentially going to map to some kind of subgroup over here, and that's what phi of K is. All right. So what do we want to do for this theorem? We want to use this theorem up here. It's an if and only if. And so what we're going to do is we're going to take two elements of phi of K. So we'll call them X and Y, and phi of K. And we want to show that XY inverse is in phi of K. All right? So we need to find the thing in K that maps to XY inverse. All right? So that's what we're going to be doing. All right, and this is how we get started. So the very first thing you should ever write down in this proof is that take my two elements in phi of K. All right, so that's going to be my X and Y. Okay. Then by the definition of the way the homomorphism is defined, just a definition of the mapping, not really any property of homomorphisms, then there exists elements A and B in K. Okay, so the fact that these things are in phi of K means something has to map to them, and that's what we're just writing down here. We're writing what maps to them. Okay, so where phi of A equals X and phi of B equals Y. All right. Now we already know that K is a subgroup, so we know that if A, B are in K, that A, B inverse is in K, and that's where we're going to start at this point. Okay, so we're going to look at phi of A, B inverse. Okay, so by the homomorphism property, which is this one right here, we're going to separate these two guys with multiplication in H. So this is going to be phi of A times phi of B inverse. Okay? And then we're going to use this property right here on phi of B inverse. So that's going to be phi of A times phi of B whole thing inverse. Okay, and then we just use what we defined up here. We know that phi of A is supposed to be X and phi of B is supposed to be Y. So this is going to be X times Y inverse. Okay, so we've arrived at XY inverse, and we just need to reason out why that has to now be in phi of K. And it has to do with the fact that K is a subgroup. Okay, so since K is a subgroup of G, AB inverse is in K. And that means we have an element in K that maps to XY inverse. So XY inverse is in phi of K, and that makes phi of K a subgroup. And once again, why is that? It's because we start off with X and Y in phi of K, and we showed that XY inverse is now in phi of K, and that's all we needed to show that this range set was actually a subgroup. All right, doodles.